Hello and welcome to this video continuing on the topic of conditional branching. So in the last video we dealt with formulating conditions and using these in if and else statements, and we created this program here which gives a guideline to the user as to whether they may or may not have to pay tax in England. We can probably improve upon this, however. Instead of having this group of people that don't pay tax and while everyone else does pay tax, most systems actually have some kind of tiered taxing. So in England, the year I'm recording this, the tax thresholds are roughly £10,000, £32,000 and £50,000. Income between around £10,000 and £32,000 is taxed at one rate. Income between £32,000 and £50,000 is taxed at another rate. And income above £50,000 is taxed at a different rate still. Wouldn't it be great if our program could reflect these different tax levels in its output? Well, of course we can do this. We just need to set up the conditional branching such that each tax level has its own branch. So the question then becomes, how can we formulate conditions to differentiate between these situations? In this case, we really want to check if the value at our income variable is within a certain range. And if you think about it, this kind of range checking actually requires combining two conditions, because we need to check if the value is above one value but below some other value. For example, to check if the value at our income variable is above £10,000 but below £32,000. And there are actually quite a few different ways that we can combine conditions in C. The two most common of these are ANDing conditions together and ORing conditions together. So let's give a more abstract example for a second. Let's say we're trying to categorize shapes. And let's say we have one condition which is the shape is square, and we have a second condition which is the shape is blue. If we want to AND these conditions together, then we want a condition which is true only if the shape is square and blue. Hence only if our two smaller conditions which make up this condition are both true. Alternatively, if we want to create a new condition which is ORing these together, then we want a condition which is whether the shape is square or blue. So a blue circle or a red square would fit that condition just fine. And in that case, we want our new condition to be true only if one of the original conditions is true. If you're familiar with traditional propositional calculus, then and OR relate pretty directly to the conjunction and disjunction operations. And while we're talking about all these logic operations that operate on truth values, I should probably also talk about the NOT operator. So as well as being able to and OR conditions together, there's also this operation called logical NOT, which is basically equivalent to negation in traditional propositional calculus. And instead of operating on two conditions like and OR, it only operates on one. And it flips the truth value of that condition. So if condition A is true, then condition not A will be false. Similarly, if condition A is false, then condition not A will be true. So okay, that's all the theory for our logic operations, but how do we actually express these in the C language? Well, the logical AND operator is written ampersand ampersand. The logical OR operator is written using two vertical line symbols or pipe symbols. And the logical NOT operator is just an exclamation mark. So if we have our condition here, income is greater than 10,000, and let's just bracket that up, then if we write exclamation mark income is greater than 10,000, so not income is greater than 10,000, then it's going to be the opposite of that condition. So if income is greater than 10,000, then our original condition would have been true, and so this new condition, not income is greater than 10,000, is going to be false. So in terms of zero or non-zero values, if the income is greater than 10,000, then our condition is now going to have a value of 0 rather than 1, because of our usage of the logical NOT operator to flip the truth value of the condition. In this case though, this isn't really what we want, so let's get rid of that. And instead let's try and nail down our conditions for the different levels of income taxation. So maybe our first condition here to deal with those that shouldn't have to pay any tax should be income greater than 0 and income less than or equal to 10,000. But in this case, because we want people that have an income of 0 or a negative income, though our income variable is unsigned for the moment, to belong to this branch, we can just have this as less than or equal to 10,000 for now. And indeed, because we've now changed the purpose of the branches, we can switch these printfs around just like that. So we're going to need to write some else ifs for our other levels of taxation, so let's just create one else if first of all, and then we're going to need another one as well. There we go. So this first else if here is going to be for the income range above £10,000 but below or equal to £32,000. And remember, these figures are just total rough estimates. I'm not an accountant or a lawyer, please do not take my tax advice. So let's make our condition here, income is greater than 10,000 and income is less than or equal to 32,000. And for now we can just give this the same printf as our else branch. And now let's formulate our next condition. So this one is going to be income is greater than 32,000 and income is less than or equal to 50,000. And again, let's just use the same printf. So at this point, this is the program pretty much complete. Let's just change our printf text though. So you may have to pay an increased rate of tax in England, and you may have to pay the highest rate of tax in England. I don't actually know if that is the highest rate or not, but let's just say it is for now. And this should just work as we expected. So if we open up our terminal here, and I'm going to compile and run, let's try £15,000. Okay, let's try £35,000. Okay, and let's try £90,000. Okay, awesome. Now actually, the observant of you may have noticed that we don't actually need the logical AND operator in this particular example. Because if we remove the first parts of our conditions here, so if I remove this part here, and this part down here, then actually our program should work just the same. Because in order to evaluate our second condition here, we need to have already evaluated our first condition. Because that's where this whole if-else-if thing works. And so actually, before we even consider the second branch for execution, we need to have considered the first branch. And similarly, we need to have considered the second branch before we consider the third branch. As a result, we know that if we even have a chance of executing the second branch, we must have skipped our first branch. And so the inputted income is already guaranteed to be greater than 10,000. And similarly for execution of our third branch, already having guaranteed that the income value is going to be greater than £32,000. Because if we've skipped the second branch to consider the third branch, this must already be the case. So in this case, we didn't actually really need our logical operators. But if we wanted to formulate the truth conditions for use outside of an if statement, for example, if we wanted to pass those truth values into a function, then we probably would need them. And actually, if I just Control Z here, back to where we were, there is a property of these logical AND and OR operators that I haven't yet shared with you, which is that they are short-circuiting operators. So actually, if we just take this condition out here for inspection outside of this program, in fact, let's just get rid of this entirely. We just have int truth equals this. So here we're just initializing an integer variable to the truth value of this condition, the 0 or non-zero value that results from ANDing these conditions together here. And actually, we better define our income variable here. Let's just say it equals 5. When I say that the logical AND and OR operators short circuit, I mean that they only evaluate conditions if necessary. So in this case, to calculate the value that should be assigned to our truth variable, the first condition that's evaluated is income greater than 10,000. In this case, 5 is less than 10,000, so this condition is false. And because logical AND requires both of our conditions to be true, we immediately know that this condition is not going to be true because our first condition was not true. We don't even need to evaluate the second condition, income is less than or equal to 32,000. We know our overall condition is false. And because the logical AND operator is defined as short circuit, this second condition will not get evaluated. But anyway, let's go back to the program we had before, and what we're going to do is we're going to have a quick look at the disassembly for this code. So if I go over to Xcode here and just hit run, we can see the particular assembly code which executes for this particular program on my particular machine and setup. And the thing that's new here that we haven't really seen before is the introduction of these jump instructions. So in these instructions here for my particular machine, the JMP, JBE, and JA instructions are all variants of the jump instruction. JBE and JA in particular here are conditional jump instructions. And these kinds of instructions are really the core of how most modern architectures implement conditional branching in assembly code. I can see that before this particular JBE instruction on my machine, we have a CMP variant instruction. This is a compare instruction, which is comparing two values, and then the JBE following this jumps the flow of execution to some other portion of code, depending on the results of that comparison. But anyway, that was just a quick interlude. Let's go back to where we were. So we've covered if statements fairly comprehensively. Let's just get rid of this program that we've written for now. But there's also another type of conditional branching in C which we have yet to cover. This is called the switch statement. So say we have some situation where we want to compare one variable to multiple values. For example, let's say we have the integer variable a. Let's say we want to do one thing if a is equal to 1, another thing if a is equal to 2, a different thing if a is equal to 3, and so on until 10. With if statements, this would require writing code something like the following. If a equals 1, do something else if a equals 2, and so on. But there's quite a lot of cruft in writing this. If we were doing this all the way to 10, we would have had to write if, else, and a equals quite a few times. And this is a primary use case of the switch statement, when we want to check if one value is equal to one of a number of other values. So let's create a proper example of this. We're going to create a time conversion utility with a number of different options. So the user inputs some number of minutes, and can choose to have that converted to one of a number of other units, such as seconds or hours or days. And the way we're going to do this is to prompt the user for their number of minutes, and then prompt them for a single character indicating the mode of conversion that they want to use. So let's declare our variables for that. We have int minutes, and then we also have our char mode. So remember, char can be used to store a single character of text. And then we can do our classic prompting the user with printf and then accepting input through scanf. So we can have a printf here, enter a number of minutes, and then we can have our scanf, and we want to scanf a %d, an integer value, into minutes. And then we're going to want a similar thing for our mode of operation. Enter a mode of operation. And we better give them some hints as to what letter means what. So let's say h equals hours and s equals seconds. And we want to accept into mode, and we want to accept a %c, a char value. And let's just squish these lines together, and then we can have our switch statement. So first off, we write our switch keyword, and then in brackets we want to write the value we want to switch on. So in this case we want to switch on mode. So we're looking to do a number of comparisons to the value at our mode variable, and then we have some curly brackets. Now inside these curly brackets we can specify a number of cases which we want our mode variable to match to. So in this case we want to do different things with the h and s characters. So we can write the case keyword, followed by the value we want to match to. So in this case the character literal h, and then a colon, and then code after this line will be what executes in this case. So for now let's just have a printf that says h. Similarly, let's create a case for the letter s, and printf s. Unfortunately though, this probably won't work as you expect. So if I compile and, oops, actually I forgot to use the ampersand for scanf, my bad, sorry, let's try that again. And actually I've just realized this isn't going to work as we'd expect anyway because of the way scanf works, so let's just reorder these, that should be better hopefully. And now if we compile and run, let's use the seconds mode of operation with 250 minutes. Okay, our switch statement seems to be working great so far. Let's try again, let's rerun. This time with the hours mode of operation, and let's use 250 minutes again. And you can see we get hs back, not just h like you might expect. And actually the reason for this is relatively simple. Because this case got matched, everything below it gets executed. We execute this line, but then continue down and flow into the next case. This is just the way switch statements work. And so to prevent this, we can use a break statement. In this context, when our break statement is encountered, it will break us out of our switch statement. And if you want, we can put one down here too, just for good practice, but we don't really need it. But this should now work as you would expect to prevent the cases flowing into one another. And sometimes actually this behavior of cases flowing into one another is really useful. Maybe we want two cases to execute the same code. So in this case, maybe we actually want to also match on uppercase s. So if our mode matches uppercase s or lowercase s here, it's going to execute this block of code all the same. It's interesting that I chose to use the terminology block of code there though, because one of the idiosyncrasies of switch statements is that the different cases really are just labels. So let's say under our s case I want to declare a new variable a. It turns out that actually, even though I've put this tab space here for formatting reasons, our case is just a label, it doesn't have its own scope. And so if we try and compile this, our variable a is kind of in a weird position between multiple branches and scopes. And so let's actually do that. If I try and compile, you see we actually get a compile time error here. Not a particularly helpful one as it turns out. Expected expression, okay, good job Clang. But this is because we don't have a proper scope here. So if you want your own scope for a case, you want to declare variables and so on, just create a block. So in this case we could just put some curly braces around here and that would do that job for us just fine. But we're not actually interested in doing that right now, so let's get rid of all that. And let's actually try and write our conversion code. So let's start with hours. So to convert minutes into hours, we're going to want to divide the number of minutes by 60. So let's do that. Let's have a printf here. And let's say %d minutes is %f hours. And then we want to feed into that first of all the number of minutes, and second of all our calculation for the number of hours, which is going to be minutes divided by the double literal 60. And we can do a similar thing for seconds down here. So %d minutes is, well actually we can use %d seconds, because any whole number of minutes is always going to be a whole number of seconds, and our calculation for that is going to be minutes times 60. And we probably have some overflow and sizing issues with that, but we're not going to deal with that right now. So let's compile that and test it out. Let's run. Okay, let's say we want to convert to hours. So I want you to give me 120 minutes in hours. Okay, 120 minutes is 2 hours. That works great. Although we should probably add a new line to the end of the printf. But let's test the seconds mode first. So seconds, give me 5 minutes in seconds. Okay, 5 minutes is 300 seconds. Cool. So let's just add those new lines quickly. And actually, it would also be kind of nice if we could have the equivalent to an else, and we could handle the case if the user inputs a mode that isn't lowercase h or lowercase s. And we can do this with switch statements using the default case. And we specify this just by writing the default keyword, and then just a colon as if it was a normal case, just like that. So maybe we can have a printf here, and let's just say invalid mode of operation. And that should work just as you expect. So let's compile, let's run, let's try the p mode of operation. And sure, 250 minutes. Okay, invalid mode of operation. And I've forgotten my new line again, let's put that in there too. And actually, let's try and add some really basic error checking in here too for our number of minutes. So it turns out scanf actually returns the number of input items successfully matched. So in our particular case for this line, it's going to return 1 if it's read the integer successfully, or 0 if there's been some other problem and it hasn't managed to read that integer. So actually, we can just shove this straight inside an if statement, just like this. And because conditions are all about 0 and non-zero values in C, we know that the if statement is going to execute this block here if scanf returns a non-zero value. In other words, if we've read our integer successfully. So what we can actually do here is if we just expand this if statement to encompass our switch statement here, then we'll only perform this switch statement on the mode if the number of minutes was read successfully by scanf. And if you want, you could put in another check like this on the scanf for the mode as well. And let's actually put an else statement with that if as well. And we can just do a printf, so let's printf failed to read number of minutes. And let's not forget that new line. So now if we go back and we recompile and we rerun, let's just say we're going the hour mode of operation. And if we try and input some text as our number of minutes, then we'll see scanf must have returned 0, and so we hit our else statement here and we get our output failed to read number of minutes. So it worked. If you wanted to actually expand this condition here, maybe you'd add a logical AND with the fact that the number of minutes has to be greater than 0 or something like that. So now for our switch statement to execute, we have to successfully read a number of minutes, and the number of minutes we read has got to be greater than 0. Now, of course, this error checking is certainly not bulletproof. We're still going to have issues with scanf, particularly sizing and overflow issues, but again, we're still not going to deal with those right now. So that is really all I wanted to cover in this video. If you want, I encourage you to add more modes of conversion to our little utility program here. So maybe you want to try to convert to milliseconds or nanoseconds or days. But really, we've made quite a nice utility here, and we've made use of these new things we've learned about logical operators and switch statements. So that is all for this video. I will see you next time.